All right, we'll get started here. Were there any questions? All right, I have a hard copy of the course info and the syllabus if you'd like to take one. I had a question about lab coat options. There are more, maybe more protective options out there. For example, when I was a student at UCLA, we were required to buy 100% cotton lab coats. At the time, it was like $70. So it was something similar to this, like a 7-ounce cotton lab coat, 100% cotton. And 100% cotton because of flame resistance. You know, there are more flame resistant materials out there. So I was taking a look at what the current requirements are at UCLA. Take a look here. There was an accident at UCLA in which a student researcher, just a new hire, somebody who just graduated with their bachelor's degree, and they were taking a gap year to work in a research laboratory before, I think, going on to medical school. But this person was wearing just a synthetic fiber sweater. And they were working with pyrophoric materials. You know, have you heard pyrophoric materials before? Pyrophoric materials just means as soon as they come into contact with air, it ignites the flame. So pyrophoric materials, you have to work in what we call an inert atmosphere. So you have boxes like the hoods there with gloves that go in. And inside those boxes, you fill them with like nitrogen gas or argon gas or helium gas to prevent any oxygen from coming into contact with your chemicals. Not only oxygen, but water too. You try to keep them dry, so oftentimes they're called dry boxes. But sometimes you don't want to work in a dry box, it's too much hassle. So this person was working with, and I used to do this as well. You just work with regular glassware, but you have little caps on them with little, what we call rubber septum. What you do is you can poke a needle in the septum and then have an outlet needle. So you put 2 needles in the septum. One needle, you inject nitrogen in here, and then it purges out the air out the other needle. And once you're pretty sure you filled this entirely with nitrogen, then you can pull out the needles. And then you have an air-free atmosphere in here. Well, sometimes we need to transfer liquid from one container to another container. So one way of doing that without coming into contact or with having minimal contact with air is using a syringe. And so I've done it many times. You just do a syringe transfer. You pull out some pyrophoric liquid here and then quickly inject it into another vessel so you can do the transfer. This person was trying to transfer some liquid, and number one, a large volume of liquid. I think the volume was like 20 milliliters. 20 milliliters of liquid in a syringe is a lot. You know, that's like something like this much. A pyrophoric material is pretty dangerous. You know, usually when I was working, it was very small quantities. If it were large quantities, I'd work in a glove box, you know, safer. Anyway, this person was doing, and a lot of these pyrophoric materials are very volatile. You know, they evaporate quickly. And so even if you get into a syringe, and the other thing is, I think the person was using a 20 milliliter syringe or like maybe a 25 milliliter syringe. So it's already at max capacity. You know, the plunger can't go out more, otherwise the plunger will fall off the end and then all that pyrophoric liquid will spill out. And so they're using too small of a syringe. You want to use maybe half of the syringe or less than half of the syringe, you know, to give yourself some safety barrier. But anyway, this person was new to working with what you call air sensitive compounds. Because when I was working at UCLA, I was working strictly with air sensitive compounds. So I did a lot and learned a lot from the people in the lab, as you go along. But this person was fairly new and doing a synthesis that somebody else did, and maybe wasn't well trained. But anyway, removed the syringe, and then liquid started to squirt out because it's very volatile, and then it caused a little flamethrower out the end of the syringe, which caught their sweater on fire, and then the rest of the clothing caught on fire. So all their clothing caught on fire. And they have these safety showers there. And so I think it took some time. There's a time delay between getting there into the safety shower. Safety shower you can use for, if you happen, there's a handle here, black handle, you pull it down. There was one instance at UCLA years ago where they had a chain on the safety shower, and there's a little valve up there. And the person went over there to pull the chain. This not only happens for fires, but for chemical spills. Say you spilled a whole bunch of chemicals on your clothing, and then you're getting chemical burns. Chemical burns can be as severe or worse than fire burns. They went to pull the handle on the safety shower, and the chain broke that time because it was corroded. And so they tested it. That person survived, though. This person, though, survived for, I think, a week until succumbing to the burns. Second and third degree burns all over the body. So after that, UCLA revamped the whole, in organic chemistry, I had to buy the lab coat because you work with a lot of flammable, not pyrophorics, but flammable chemicals. But now they're requiring everybody. Maybe it's relaxed a little bit. But gloves are required at UCLA. Vinyl, I guess vinyl are okay, but when you look, there's charts, chemical resistance. Usually you look at these charts of chemical resistance. For certain chemicals, vinyl might be okay. Other chemicals, it's not good. The same thing with latex and nitrile. There's a chart you can look at depending on what you expose the gloves to. But I had these. I wore natural rubber latex gloves as well, plus bigger gloves. Viton gloves. I used Tyvek gloves. I've used Beetle gloves. Used the didn't use an apron, but it looks like they aren't requiring 100% cotton. So it just says, well, the generally used chemical, biological, radiation, and physical hazards. So just the standard lab coat. Here you have the flame resistant. This would be 100% cotton, like the 7-ounce one. In fact, I think the image is the same. Okay. Flame resistant, such as flame resistant cotton or Nomex. Nomex is going to cost you a lot more. Nomex is like the fire suits with the fire fighters wear. All right, this is, I guess, for graduate students, they require flame resistant now. For undergrads, it looks like they don't require it. I also had this, when I was working with a lot of reactives, I'd wear my lab coat and then I'd wear this Tyvek thing around it. And then I had Tyvek sleeves, Tyvek gloves. Tyvek is a pretty good barrier for different things. But I guess it's biohazard. It feels like you're in a sweatsuit because they don't breathe. You end up feeling like you just came out of a sauna on those. But if you're interested, the price on these 100% cottons has gone way down. mean, that price is pretty good, I think, for this. Our bookstore has it too, but when you look at this, wow, 100% cotton. I don't know how thick it is, but $27 for 100% cotton. So, you know, versus a $15. Mine was a $15, but if I had a choice, I probably would have bought this instead. You know, a little bit more expensive, but maybe a lot nicer. But I don't know. You know, it could be pretty thin. It's nice. All right, so that was something about that. We aren't going to need the lab. You know, the personal protective equipment for lab until let's see, today's the 22nd, so not until next week on March 1st. That's when we start our first lab. We're going to check in on Thursday. Why are we waiting so long to start lab? The main reason why we're waiting so long to start lab is because in the past, this class, you know, to get the ad situation sorted, normally there's like a waiting list, but you know, this semester is great because there's no waiting list. But normally there was a waiting list, and so what I did was I gave people some time to sort their schedule out and then start lab. That's why we're starting so late, but it's already in the schedule, so it's fine. All right, any other questions? The other thing is, normally I don't start lab in the first week, or, you know, to reduce, to get ahead a little bit. As people, you know, the people's schedule, they're still trying to work out their schedule, so I have people dropping and whatnot. All right, Wednesday there's a chance that I have to leave for a funeral, fortunately. So if that happens, then what I'm going to do is just cancel class, and maybe we'll have a session, a recorded session or something. I'll post. Or we can have a live session at an alternate time. It depends on what time it is, you know. They're still trying to work out the schedule, the cemetery. Since yesterday. The Zoom office hour, no, but the regular office hour, yeah. The regular office hour is just going to be after class. On lab days, Tuesdays and Thursdays, just stay after class, you know, for as long as you want. The Zoom, though, I think what we'll do is just schedule that, not as a regular, but just as needed. Just schedule that. Let's see. What I was thinking of doing for the Zoom is just having, is some people had mentioned that that they might need some additional help with certain things. So what we could do is not have like an office hour, but maybe like a review / help session instead. If you're interested in something like that, then let me know. You know, last semester I did these, but you know, out of a class of, I think, out of a class of maybe 60 students, only about 2 or 3 people actually attended that. So, if you're interested, let me know the time you're available, and I'll schedule it. Oh, question?
Oh no, I thought you said the time already.
Oh no, I haven't set a time. I'll pass out a little survey card. That's what I was supposed to do last time. Just tell me, you know, the time, the best time, or the times you're available. I'll pass these out later. So Wednesday, I won't find out until later today. And so when I do find out, I was thinking I'll send out an email or post it on Canvas, to let you know if whether to come to class tomorrow or not. So keep an eye out for that. I'll probably just post it on or send out. What do you guys prefer, post on Canvas or send out? Email? All right, I'll send out an email. So we'll leave that as a question mark. If I find out before the end of lab today, I'll let you know. All right. So let's take a look at Lewis acid-base reactions. All, 100% of acid-base reactions fall into the Lewis acid-base category. This is the most broad definition of an acid-base reaction there is. But we don't look at all. If we look at the universe of acid-base reactions, Lewis is the entire universe of acid-base reactions. So really, to understand acid-base reactions, we just need to understand Lewis acid-base reactions. But the problem with Lewis acid-base reactions is sometimes it's more complicated, and therefore it's not as easy to understand. And so what we do is we'll subdivide this. If we look at Arrhenius is a small subset of acid-base reactions. So this would be the Arrhenius, which would be like maybe a sun in the universe, But Bronsted would be a bit bigger. Bronsted would be like a solar system or galaxy or something. Say galaxy. And so Bronsted is a bit bigger, but not the whole universe. But the thing about Bronsted is so much easier. If we want to know the acid strength, it's easy. The acid strength is in the Bronsted acid chart. HClO4 is at the top, methane's at the bottom. If we want the Lewis acid chart, there is no equivalent of the Lewis acid chart. There are certain categories of Lewis acid-base reactions. One of them would be, which don't fall under Bronsted, but an alternate part of this would be what we call, transition metal complexes. Transition metal complexes, this is in chapter 24. And here we do have a ranking. When we're looking just at transition metal complexes and these Lewis acid-base reactions, then we can rank the bases in terms of base strength, and we can rank the acids in terms of acid strength. But the ranking is a bit more complex. How we do it, because it's really dependent on the acid and the base. For example, one base might be a very strong base for a particular acid, but if you have a different acid, which is another transition metal, it might not be so great. And so the same base might behave strongly towards one acid, but not as strongly to another. And so what are these acids? So we're going to look at these transition metal complexes now. So we could look at things like a calcium ion, for example, Ca2+, or things like a lead-2 ion, Pb2+. These metal cations are electron pair acceptors. Electron pair acceptors are acids by the Lewis definition. And so these are Lewis acids. They don't have to have a proton, but Lewis acids are just electron pair acceptors. And they're different. When you think about calcium, you visualize a small, right? Something that's, although lead is small too. But when we think about it, when we think about calcium 2+, we think about small hard ion. So think calcium 2+, small hard ion. Whereas lead is a soft ion. Does that make sense at all? So heavy metals are kind of soft, on the softer side. You know, these calcium, like group 2s, you know, and some of the smaller transition metals, and aluminum 3+ would be like a hard ion. Mercury would be like a soft ion. And so this brings up something called, when we want to understand strength, Lewis acids and bases. Then what we use is we use something called HSAB, or quantum mechanics. You know, if we do quantum mechanics, and that's okay, we can do quantum mechanical calculations, but it's not so easy having to do quantum mechanical calculations for everything. And so instead, this kind of brings it to a different way of analyzing it, just by estimating certain things. So HSAB, what does that stand for? HSAB is equal to hard, soft, acid, and bases. And so there's a very simple rule in terms of understanding, you know, what reactions are favorable. The simple rule is this: hard acids like hard bases. Soft acids like soft bases. So let's compare things. Let's compare a 2p orbital. You know, can you visualize a 2p orbital? Like a 2p orbital. How would a 2p orbital compare to, let's say, a 4p orbital? If you had a 4p orbital, what would be one of the key differences between a 2p and a 4p? It actually doesn't matter if it's up and down, left and right, you know, sticking out of the board, going into the board. You know, those three orthogonal orbitals are equivalent in terms of energy. And so it doesn't matter if I wrote this one up and down, it'd have the same energy as left to right. It's larger, yeah. The 4p orbital is going to be a lot bigger. You know, more like something like this. about 4 times bigger, let's say. Which of these would be more polarizable? Do you guys remember polarizability? Polarizability? What did you use polarizability for in Chem 1A? Anybody recall? Well, in terms of bond polarity, in terms of, do you guys remember London dispersion forces and the stronger the London dispersion force occurred for things with more electrons. More electrons meant more orbitals meant bigger orbitals meant more polarizable orbitals. Polarizability is just the ability to distort the electron cloud. And so here, the electrons are held tightly and close. That's hard. Here, the electrons are loosely held. The electrons are loosely held. It's a big orbital. So the electrons are free to roam around that with 95% probability, right? Big orbital like this means the electrons are a lot less in terms of being tightly held or confined to a volume. And so what would you say is harder? This orbital or this orbital? Electrons in this orbital versus electrons in this orbital? Yeah, this should be soft, polarizable. Electrons are kind of free. This is going to be hard. Do you see that? And so this is the basis of this hard, soft. The basis is in quantum mechanics with the orbitals and how the orbitals interact. When we're thinking about molecular orbital theory, do you remember LCAO? Does that ring a bell? LCAO. All these acronyms. If you recall, this is based, HSAB is based in LCAO. Could be, potentially. LCAO stands for linear combination of atomic orbitals. Linear combination of atomic orbitals, where's that from? Or where does that click? Well, it was versus this. There are 2 ways to describe valence bond theory versus MO theory. MO theory, the atomic orbitals undergo linear combination of atomic orbitals, so they add up quantum mechanically, and what gets spit out are new molecular orbitals. So you take 2 atomic orbitals and you end up with 2 molecular orbitals. You remember doing the sigma 2p, pi 2p, pi star 2p, sigma star 2p? Well, that's LCAO. So what we're doing was generating the MOs. Versus in valence bond theory, and valence bond theory is just overlap of atomic orbitals. So you don't get rid of the atomic orbitals, you're just overlapping the atomic orbitals versus a combination of the atomic orbitals to generate new molecular orbitals. And so when we're generating, molecular orbitals, it's better to have similar sized orbitals. So if you take a gigantic orbital, like a 4p, and then try to do a linear combination with a 1s, a 4p and a 1s aren't going to have as favorable, because what happens is you take those 2 orbitals and you generate this kind of thing. Do you remember doing this kind of MO diagram? Where you create an anti-bonding MO and a bonding MO from 2 AOs. So this is an AO here, this is an AO here, this is an MO, and this is MO star. Well, if you have good combination, then what happens is the bonding orbital drops even further in energy. So it becomes even more favorable when you do that. But the anti-bonding, on the other hand, goes up, because the energy is conserved. But it depends on how favorable this linear combination is, which will stabilize the molecule. We aren't going to get into this here at all. This is just FYI, well, what we're going to do is we're just going to look at the data. We're not going to get into the theory of this. We're just going to look at some observational data and then just try to understand things based on that simple observational data. But when we do that, there's going to leave a lot of unanswered questions, probably. Like, yeah, why is this a better acid? It doesn't make sense. Or why is that a better base? It doesn't quite make sense, but it makes sense in the grand scheme of things when you look at it quantum mechanically, which we aren't going to do. And so you're just going to look at it and say, okay, that's what the data shows. And so most of these occur for transition metals, but we could have it for other things as well, other cations. And they need not be transition metals. So, for example, is aluminum a transition metal? Aluminum is not a transition metal, but we form complexes with aluminum in this Lewis acid base reaction. In fact, very, very common. But, even though aluminum is not a transition metal, it's discussed in chapter 24, and we look at the complexes of aluminum. So it need not. Same thing with calcium. Calcium is not a transition metal, but will form complexes with that as well. And so the acids are metal ions, metal cations. Metal cations. The bases are a lot more varied. The bases, all they have to have is a lone pair, and then it's considered a base. So let's look at one base really quick. Probably starting off with the most complicated base discussed in our book. This base, EDTA4-. EDTA4- stands for ethylene diamine tetraacetate. Actually, you got to stay on top of the nomenclature. This is ethylene diamine. That's all one word. Diamine, and amine here only has one M. Tetraacetate ion. When this ion likes metals like this, calcium 2+, lead 2+. This is the reason why they used it as a medication for lead poisoning, because it likes lead. It likes lead more than it likes calcium. So if it's with calcium, then, but it'll react with both, like that. Is that 2-year-old? Got the intravenous sodium EDTA. Well, it's going to attack calcium and lead. Problem is, you want to get rid of the lead, but you don't want to get rid of the calcium because you have to have the proper balance of ions. If the ion balance gets all screwed up, then it can cause some serious health consequences. Okay, so something like EDTA is going to attack. But if EDTA already has calcium, like for example, if we started off with calcium EDTA, then at least it has calcium, because it doesn't like sodium nearly as much. Sodium is kind of a big ion, and it doesn't have a very high charge. So sodium ion is not a very good Lewis acid. What makes a good Lewis acid is what? You want a high positive charge density. And so small ion with a high charge, aluminum 3+, high positive charge density, because aluminum is a tiny ion. It's got a 3+ charge. But sodium ion's big ion, so the electrical attraction is pretty weak. We're looking at these electrical attractions. And so sodium EDTA, if EDTA is with sodium and it sees a calcium there, it's going to attack the calcium because it's going to want the calcium. Right? If it's already calcium EDTA and calcium's not going to change anything. But if that calcium EDTA stays a lead, then it's going to like the lead more. Big soft ion like that. Will like it more. So let's take a look at the EDTA structure. So let me just draw this out again. CH2, since we ran out of time. we're going to put the ethylene and then the two amines here. The amines are like ammonia. Let me talk about amines over here briefly. There are lots and lots of amines out there. And they're all ammonia-like, so they're all base, Bronsted bases like ammonia. And so ammonia is the prototypical amine, and then we have lots of derivatives of this. For example, we have CH3NH2. So we lose a hydrogen, replace it with what we call methyl. This is called methylamine. We could also have CH3,2NH. This is where we take off two of the hydrogens and replace that with a methyl. Now, carbon and hydrogen have very similar electronegativity, so these are going to behave all somewhat similarly. We could take out all the hydrogens and go with 3 and just have an N. And the crucial point is that N's got to have a lone pair, which it does. And that lone pair can be donated. The other crucial part is that N has to have a negative charge. In this case, it's going to have a partial negative charge. And so each of these N's is going to be partially negative. Now, partial negative charge is displayed in quantum mechanics with red. This is kind of weird because, usually you think of negative charge, you think black, but not red. I don't know who designed the color scheme for this, but not a battery person. So the delta minus on the nitrogen is all about the same because electronegativity difference isn't so significant. And so two things we need. We need a negative or partial negative charge, and we need a lone pair. And that makes it a Lewis base. So amines are good Lewis bases. However, we would not call this an amine. So if I had NF3, so for example, I was looking for ammonia in a chemical catalog, and I couldn't find it. And I thought, why doesn't this chemical company, supply company, not have ammonia? Ammonia is such a common chemical. And then I figured it out. It was a European chemical company. And I figured it out because they didn't call it ammonia. Do you know what they called it? I was looking for ammonia, but they called it nitrogen trihydride. So if I did find it, nitrogen trihydride, NH3. They just didn't call it. What about nitrogen trifluoride? Would this be classified as an amine? Why or why not? I'm sorry?
I think no, it wouldn't because there's no hydrogen.
Well, this is classified as an amine, and there's no hydrogen on the nitrogen. But there is hydrogen over here, but that's not the methyl group is not doing anything for the Lewis base part.
It's not negative.
Yes, it's not negative enough. In fact, what do you notice about the nitrogen? Do you see, when you look at these two, nitrogen trihydride versus nitrogen trifluoride, do you see their universe apart? Can you look at those two and go, wow, those are totally different chemically? Why?
The fluorine is more electronegative, so it's going all the electrons.
Yeah, right. The fluorine is more electronegative. In fact, the delta minus is going to go on the fluorine, not on the nitrogen. In fact, the nitrogen is going to be delta plus. Well, if the nitrogen's delta plus, is it going to be so willing to donate its electron density? No. In fact, take a look at the oxidation state. What is the oxidation state on nitrogen in ammonia? If we look at the oxidation state of nitrogen and ammonia, it is -3, which means ammonia is flammable. This is pretty electron rich. This is flammable. Don't burn ammonia because it can generate lots of, if you burn ammonia, it can generate lots of oxides of nitrogen. Oxides of nitrogen are toxic, like nitric oxide, nitrogen dioxide, N2O4, dinitrogen tetroxide, et cetera, et cetera. Those are all oxides of nitrogen. Not only that, if you burn it in methane, and it depends on the stoichiometry of it, you could also form hydrogen cyanide, burning it in methane. Hydrogen cyanide has the odor of burnt almond. So if you smell burnt almond, that's not good. It's could be hydrogen cyanide gas. But if you burn something like nitrogen, yeah, that's going to generate all kinds of toxic products, probably a mixture of them. So do it in the hood, if you do anything like that.
How long does it take for something like that to dissipate?
Like hydrogen cyanide?
Yeah.
Depends on ventilation. This lab is supposed to have 5 room changes per hour. This is why when they were proposing this, I was thinking, is this really going to make a big difference? They wanted the HEPA filter. This is more than HEPA filtration. This is UV in there and some other stuff. But this is a very nice filter. But I think in this lab, I'm pretty sure it's 5 room changes. I have to double check that. But that means 5 each hour we get 5 changes with fresh air. So all this air in here is purged out, and then we get a new batch of air from outside, which is great ventilation. Indoor air quality depends on where you are, because COVID, this is the lockdown. The lockdown kept everybody inside. I remember in Manhattan Beach, there's that paddle boarder out there. You got the big fine. And then all the parks were closed. And then I guess Garcetti went hiking, and then he closed all the hiking trails, which I thought at least I'll be able to go hiking. But I wasn't even able to go hiking because at the trail, they put a $2,000 fine, like the paddleboarder, for trespass. So, but it turns out that outdoor transmission is way safer because it's got great ventilation, but you keep everybody cooped up inside, and it's going to promote transmission. But anyway, so it doesn't take long to dissipate in this room, but if you do smell something, the best thing is not to risk it. The best thing is to go out. And we do smell stuff in this chem a lot more before, because I give simple rules, like, for example, do not mix acids with sulfides. Do not mix acids with sulfides, because you're going to generate a rotten egg odor. If you generate a rotten egg odor, that's hydrogen sulfide, which is toxic at the part per billion level. But every semester, somebody mixes acid with sulfide and then fills up the lab with rotten egg odor, and then we all evacuate. That happened almost every semester. And then we finally got rid of the sulfides. So we're not going to work with any sulfide salts, because it's just too, not worth it, actually. But the bad point about that, I didn't want to get rid of the sulfide salts, but I think most of the department did. The bad thing about that is, we're trying to train ourselves to work with hazardous materials safely. We don't want to say, okay, this is hazardous, so I'm going to keep away from this. Like driving. Driving's too risky. I'm not going to drive anywhere because it's just too risky. The probability of getting in an accident or something like that, it's the same thing. You work with hazardous chemicals like gasoline. Gasoline is very flammable. You could end up having a very bad accident there. But, what we want to do is we want to work with these things safely. Like, for example, the accident at UCLA was totally preventable. If that person just had a little bit more experience, and knew how to handle dangerous chemicals, that could have been done totally safely. I have a friend that I was working with, prions? Prions are what causes like mad cow disease. And these prions are just these molecules that once you get it in, then, it's like a death sentence, basically. And then I'm thinking, this person, it's crazy, because you're thinking, that's so risky. Why do you want to even touch those? Or, for me, I just want to stay away, And nobody should touch those, but, you know, there are people that touch those and touch those safely without killing themselves, you know? And so it's the same thing, you know, when the original proposal for locking down all the labs, I was thinking, you know, the lab is pretty safe, 5 room changes per hour. If we had N95 masks and then we have goggles, you know, N95 mask and goggles and the ventilation in the lab, maybe we could do it, and then maybe make it less crowded, the lab, and then I think we'd have done it safely without undue risk. You know, it depends on your risk level too, because there are some people that shouldn't work with power fork materials, you know, and then there are people who can be trained for that. It depends on your risk level. You know, if you can tolerate a little bit of risk, then maybe you could continue. But if you can't because there's high risk, you know, either health issues or family issues, then you shouldn't, you know. But it's like shutting down all the roads, you know, getting rid of all the cars, you know. It all depends on the risk tolerance and that equation that goes into it. But anyway, I don't really want to smell H2S, you know. And we did have cyanide because cyanide is an excellent Lewis base. And so we did use cyanide and arsenic and a whole bunch of other stuff for years. And then I you know, had to keep on everybody to make sure that they didn't do anything dumb. But, you know, for the most part, it was okay. Nobody died. You know. So maybe got headaches because when you start smelling H2S, because I used to work with a lot of H2S. When you start working with H2S, you get a headache, pounding headache. But yeah, going back to this though, it's -3 for ammonia. What is it for NF3? +3. Do you see? This is a world of difference. This isn't very flammable. You know, it could, you know, because it could go to +5. So it could lose 2 more electrons. But it's not going to burn like this. Well, not only that, this is not going to be a Lewis base. This is not going to want to donate the pair of electrons. And so these are excellent Lewis bases here. This is a very, very bad Lewis base. Yeah. So it has to do with the charge on the nitrogen, basically. Yeah. So let me erase this here. Or actually, I don't need to erase it just yet. Let's go over here. So we are going to have these 2 amine groups, and the amine groups are just going to be bonded to carbons, like this. Yeah. So here, this nitrogen has no hydrogens. Well, it doesn't need hydrogen. But will this be a good amine? Will this be a good Lewis base? Yes. The answer is yes, because, I mean, these are carbons. Carbons are very similar to hydrogen in terms of electronegativity, so no big deal there. So this is going to be CH2, C double bond O. Oh, now this is acetate. So there's going to be a negative charge on that group there. All right, if you had a choice between this, we know that this isn't really accurate because there's resonance form for this and there's a resonance hybrid. So in reality, both these CO bonds are equal, and in reality, both of these oxygens have the same charge. You know, we say -1/2 on each, which doesn't mean half an electron. It's just how the electron cloud is spread out, distributed. But if we froze this, we can't even freeze this. Let's say we had this scenario where we had a terminal oxygen like this versus a terminal oxygen like this. So let's say there wasn't any resonance forms, and which of these 2 oxygens would be a better Lewis base? The one with the negative charge or one with the partial negative charge? With the negative charge. Now, maybe both of these can attack, but if both of those attack, what happens is we end up with ring strain. And that is either one or the other can attack. When we talk at Lewis acid base, in Lewis acid base jargon, the base always attacks the acid. You know, with the lone pair. So when we think about this, here, both of these can, because if both of those attack, then we have something called a ring strain. So there are carbon rings, you know, let's just talk about rings for a second over here. Something like this, cyclo. This is called cyclohexane. And actually, there are 2 hydrogens on each carbon. So rather than write it out like this, I'll just write it like this, CH2s. So this is cyclohexane. There's very little strain. Cyclohexane is very common. It's a liquid. But when we get to cyclopentane, you know, pent is 5 carbons. No big deal. Cyclobutane becomes a problem. In cyclobutane, what should the bond angles be? In cyclobutane? 90. What are the normal tetrahedral bond angles? Or bond angle? What's the normal tetrahedral bond angle? This is a tetrahedral sp3 carbon. The tetrahedral sp3, 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 sp3. What's the sp3 angle? Not 120. sp2 is 120. Not 90. Okay, this you need to know. If you're going on to organic chemistry and you don't know sp3 and sp3 bond angle and tetrahedral, you're going to be in trouble. It's the most common angle and hybridization in organic chemistry. The tetrahedral, remember the tetrahedral, there are different ways of drawing it. I usually draw it like this. You know, and the bond angle, this is like a sphere, it's spherical symmetry. And so if you have 4 groups, you want them as far apart as possible, you adopt the tetrahedral geometry, which has an angle of
120.
not 120, 109.5. 109.5, that's rounded to, this is rounded to 4 sig figs. It's 109.47, something like that. If we round this to 3 sig figs, it's what? It's not 110. If we round this to 3 sig figs, it's 109. And so normally people say it's 109. You know, if you want to get more precise than 109.5, then 109. This is 90. This causes a lot of strain. This is ring strain. This is unstable. Cyclobutane is unstable. Likewise, cyclopropane is going to be a 3-membered ring. Prop is 3 carbons. What do you expect for the bond angle for cyclopropane? It should be 60 degrees, but these are tetrahedral sp3 carbons. You know, they got 4 groups attached. According to Vesper, those 4 groups should be as far apart as possible. Being as far apart as possible means they adopt a 109 tetrahedral geometry. But this is 60 degrees. That's what we call strain. You know, in other words, the orbital overlaps. You know, normally when you have orbital overlap, this is valence bond theory. We're going to take an sp3 orbital and an sp3 orbital, and we should overlap those sp3 orbitals straight on like this. But if they're overlapping at some oblique angle, you know, some odd angle, it's not going to overlap very well. You aren't going to get that, what we call the internuclear electron density to hold the atoms together effectively. It's going to be outside the internuclear axis. You know, we already have pi bonds which are outside the internuclear axis. But, you know, this is okay. So this is 60. This is very unstable. So what happens is both these oxygens can't react. So let's say if I have a lead here, 2+ like this, and I have both those oxygens come to form, what kind of bond is that? Yeah. Well, it's a single bond. You call it a coordinate covalent bond or dative bond. But when we form this kind of bond linkage here, this would form a how many membered ring? This would be a 4-membered ring. 4-membered rings are highly strained, so it's not going to happen. So we have to pick one or the other here. One or the other. And if I pick one or the other, which one would be better? This one with the negative charge or this one with the partial negative? Well, the one with the negative charge is going to be a better base. It's like this. Which one is a better base? Hydroxide with the negative charge? That's a formal charge. Or water with a partial negative charge? Yeah, hydroxide is going to be a better base than water. Partial negative. Bases we want negative. Acids we want positive. This goes for Bronsted too. You know, Bronsted acids are going to have the bigger delta plus. You know, that makes a good Bronsted acid. Bronsted bases, you want the negative charge concentrated. Okay, so let's go ahead and do the rest of this. There's my second acetate. Here's my third acetate. Here's my fourth acetate. So that gives this ion a net -4 charge. When I add up the formal charges, all the other formal charges are 0. So this is a very interesting, you know, what we have free rotation about single bonds. Double bonds, there's no free rotation because if you tried to rotate a double bond, you'd have to break the pi-pi bond. You know, and that's not going to happen. But around these, you know, this would be like this would be a sp3 sigma bond. You could rotate the orbitals and still maintain the orbital overlap. Yeah. All right. So what we're going to do is we're going to look at this. What we do in Lewis acid-base reactions, we look at individual atoms. You know, we don't look at the whole ion. And so what we see here is this would be a good base. 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 This. And so, like, we have, like, you know, monoprotic, diprotic, triprotic. We also have basic, like monobasic would be like sodium hydroxide. Dibasic would be like calcium hydroxide. But what would this be in terms of Lewis? This would be a hexabasic. Do you see a hexabasic? This has 6 base donor atoms. And so we could say hexa, I'll just use that, basic. 6 donor atoms. Now, I say donor atoms, this electron pair donor is the base. In one ion. And so let's take a look at, let's put a lead here, Pb2+. And what's going to happen is, okay, this thing is seeking, you know, Lewis acids in solution. So you release this, and it's looking, and then it sees this, right? Sees that. Now, which one is a better base, nitrogen or oxygen? You think about it. And so when you think about like hydroxide or, you know, hydroxide versus ammonia, which one's better? Hydroxide. And then you think of hydroxide, well, that's kind of like this, isn't it? Negative charge there. It's a little bit different because this carbon is kind of positive, what we call electropositive, because of this terminal oxygen, the inductive effect. And the inductive effect means this is less basic. You know, if I compared hydroxide with acetate, which one's a better base? Hydroxide versus acetate? Hydroxide versus acetate, which one's a better base? Hydroxide is. Why? Because hydroxide has more negative charge concentrated there. hydrogen versus oxygen, who's going to win? Oxygen. So you got all that negative charge cloud concentrated in the oxygen here. Now let's take a look at this. When we compare this one, you think carbon and hydrogen are similar, right? But look at this carbon here. This carbon has another oxygen bonded to it, which is going to suck electron density away. So the inductive effect is going to work here in this way. There are two ways of describing this. One way of describing this is inductive effect. There's no inductive effect here. All that charge density is going to oxygen. So the arrow's pointed there. However, over here, what's going to happen is this oxygen sucking electron cloud from carbon, which means, usually oxygen versus carbon, oxygen wins. But now the carbon is different. The carbon is getting, less and less electron density around it, making it more electropositive. In fact, one way we can think about this is what's the oxidation state on this? So this is a carbon-carbon bond. There's no these hydrogens are terminal over here. So carbon versus carbon, it's a tie. So that's one electron. This one, both electrons go there, both electrons go there. So this carbon ends up being +3. That's not your normal carbon. If you have a +3 carbon here versus, let's say, a 0 carbon, it makes a big difference. And so this carbon is going to put up a much more significant fight here. And so this is why in the inductive effect, the arrow points towards carbon. It still might point a little bit towards oxygen. This is just showing that the balance has swung towards carbon. Carbon still might not be the winner, but it's significantly stronger now, which means that this negative charge is being sucked into here rather than being focused or localized on this oxygen. It's being delocalized. Have you heard localized versus delocalized? Localized versus delocalized, very important in this stuff, and especially in terms of acid-base strength. And so acid-base is going to be much weaker base than hydroxide, but that's okay. This is still going to be okay. Now, compared to this, and so here comes the first rule. When we're looking at transition metals or metal cations with electron pair donors, the strongest Lewis base, and let's talk about this over here. This is how we're going to rank them. Lewis base strength is not going to be looked at individually. In terms of Lewis base strength, the strongest. Should you start off with the strongest? Or start off with the weakest? I guess start off with the strongest is usually with carbon donor. The strongest would be carbon donors. And so the best Lewis bases would be things like cyanide. Cyanide has a carbon triple bond to nitrogen. There's a lone pair on carbon, the lone pair on nitrogen. Carbon ends up with a negative formal charge. This is weird because nitrogen is more electronegative. But carbon ends up, why? Because of the octet rule. Carbon monoxide, same thing happens here. Carbon monoxide has a positive charge and a negative formal charge. Where is the positive formal charge? Well, automatically, you would think that the positive formal charge would go on carbon and the negative formal charge would go on oxygen because oxygen is more electronegative. But tell me what the formal charges work out in this to be. Carbon is -1, that's correct. And what's oxygen? +1. Now this is not right? This is backwards of what you would expect. But it's backwards of what you would expect because if I took these to 0, then what would be violated? if I took these to zero, I could easily take these to zero by just double bonding. If I just did a double bond here, this goes to zero. What would the formal charges here be? The formal charge, yeah, this one would be zero and this one would be zero. Everybody would be happy except what's violated. Octet rule is violated. Only way to make an octet is to have this screwed up formal charge situation here. But that screwed up informal charge situation makes carbon monoxide an excellent Lewis base. So cyanide and carbon monoxide are very powerful Lewis bases. These really seek out Lewis acids. One Lewis acid is the in your blood. You know, you have iron in your hemoglobin or hemes. You have iron there, and carbon monoxide and cyanide love that. They want to bind to that iron, form a strong bond, not let go. Okay, so carbon donors, and then the next best Lewis base are oxygen, or not oxygen, actually nitrogen donors. This is a bit odd too, because when we think about it, like hydroxide versus ammonia. Hydroxide versus ammonia, which one's a more powerful Lewis base? Well, I don't know, but I know which one's a more powerful Bronsted base. Hydroxide versus ammonia, which one is a stronger Bronsted base? Well, in terms of Bronsted, hydroxide is a strong base, ammonia is a weak base in terms of Bronsted. In terms of Lewis, ammonia is a strong base, stronger than hydroxide. So if I were to compare hydroxide and ammonia, ammonia is better. Lewis base. And so the nitrogen donors go next. That would be like ammonia or the amines. So the amines are next best. And these are going to be better than the oxygen donors. The oxygen donors would be like water and hydroxide. Which are better than the halogen donors. The halogen donors would be like fluoride, chloride, etc. So that's the ranking there. So if I had lead here, sitting here, and EDTA is a medicine for lead poisoning, then what's going to attack that lead? Well, we expect to attack the lead first would be nitrogen. You know, nitrogen is a better Lewis base. So we'd expect the nitrogen to attack. Let's put the nitrogen on the top here. Can you do that? Let's see how best to draw this. So what happens is this. So I have this lead over here, and the base attacks the acid. So in this case, the base being the nitrogen, here, this attacks the acid, being lead. And so this was once a lone pair is no longer a lone pair. That is going to be a bonding pair. So the lone pair gets converted into a bonding pair. Okay, then what's going to happen next? What's going to happen next is this is going to wrap around. You see the CH2, and there's another nitrogen. So what happens is this is like a noodle, and it can wrap around and bind that other nitrogen. So let's go ahead and do that. So how am I going to do that? Well, we're going to go to an adjacent position. And so let's go ahead and I'm going to bind this. How should I bind this to make it okay? This is going to be a bond that's dashed in. And so what we're going to do is we're going to go CH2, CH2, N. And so now we've binded this, what we call the ethylene diamine. So one nitrogen bites it, the next nitrogen bites it. So it's like a claw. Do you see that? If we have two things binding it, then it is like a claw, because when you have something like this bind, it's very hard to break off. Think about trying to break this off. So if I broke this bond here, let's say I break this bond, it's still attached here, right? And so I go to break this bond, but I need to break this bond next. And so while I'm breaking this bond reattaches. This is an attraction. And so, boom, it reattaches. And so now I've broken this bond, then I go back to break this bond, and then this bond reattaches. Do you see the predicament I'm in? And so what we call this is, anything that binds two places is called a chelating agent. Chelating agent comes from like the claw, crab claw. Crab claw binds you, it's hard to pull off the crab claw, basically. Well, it's the same thing here. This is what we call chelated. Chelated is good because if it's chelated, then the lead can't cause damage to your proteins or whatever else can cause damage to. But not only that, what you have these things dangling. We have two acetates dangling on the nitrogen. And these two acetates that are dangling on the nitrogen, well, one of them might wrap around and bind to the lead. And so let's do that here. And so that's going to be like this. Let's see which way am I going to go for this one. I'll go like this. So it's going to go nitrogen, CH2C, CH2C with a double bond O, this, and then an O. Let me try to redraw it a little bit better here. I should have drawn these first. Let me draw this. There. This is wedging out, so this is dashed in, that's wedged out. So this is another one. And then we have another one of these CH2 groups. I'm going to try to draw it like this. That's going to go down and bind it to the bottom here. So this is not a very good drawing, sorry. Let me try to draw dotted. Okay, so there's another group that comes in. Actually, you don't have to draw this so accurately. Okay, then we have this other one up here. CH2, C double bond O. And then we're going to have another dashed in O here. And it's going to come like this. One more. One more. I gotta bring this one to the front, and then one to the back. So I have one more CH2, C double bond O, O here. Yeah. Okay, and then I'm gonna have one more here. Shoot. I didn't do it in the right configuration. But etc. We'll just leave it at that. You don't have to draw something like this. I screwed this up because the way it links is I can link two adjacent sites. This comes out to octahedral. And so I can link two adjacent sites, but I can't link two opposite sites. And so I just got it the wrong sequence. I should have checked it, the sequence. But the next one I'd have to do is off this one, and that's going to go to the opposite site. And so I screwed this up. But I don't want to waste any more time with this. But do you get the point? The point is this. We have different names for this. So let me see. This is going to be another oxygen here. If just the two nitrogens bind into this, we call it bidentate. Dentate means teeth, and so it has two bites in there. But this one is binding to 6, so we call this a hexadentate. Base, and the base we're going to name ligand. And so this is a hexadentate ligand. And so basically it's just going to encapsulate the lead. And once this encapsulates, is it going to be easy to break off? No, it's going to be very difficult to break off, so this is why people are thinking it's effective. I mean, they use EDTA for lead poisoning, but they also use EDTA as a food preservative. Do you know how they use it as a food preservative? What EDTA does is it binds to magnesium ions, and bacteria needs magnesium ions. And so if EDTA strips all the magnesium ions out of the mix, then the bacteria can't survive. And so the bacteria eventually end up dying because of a lack of magnesium, because EDTA has a preferential, once it binds hexadentate to magnesium, it's not letting go. And so, that's the reason why. Okay, so let's take a look at some simpler ones. This is the most complicated one. And so this is as big as it gets, the hexadentate, but there are a lot simpler ones. And so we're going to look at a few things that we need to consider for transition metal complexes. This is what we call an octahedral complex. But there are other kinds of complexes that we also encounter. And so let's just look at the structure. I'm going a little bit out of order. We have linear complexes. So let me give you some examples of linear complexes. Would be something like this. The silver in there and attached 2 ammonias to this. That would be an example of a linear complex. Now, why don't more ammonias attack? Well, they don't. You would expect you can have a whole bunch more ammonias attack this. Looks like the silver is pretty unprotected. But no more ammonias attack this. This is it. We call this one silver. The name of this is called diamine with 1 M, silver, Roman numeral 1. Even though silver only has 1 charge, that's +1, we still add the Roman numeral 1. So this is the diamine silver 1 ion. And the weird thing is, it doesn't even have to be an ion. You could actually just have neutral metal atoms be attacked by Lewis bases as well. Like carbon monoxide attacks certain neutral metal atoms. We could put cyanides on here. So we have a cyanide, a silver, and another cyanide. Now the weird thing is the lone pair is being used for the bonding. The lone pair is being used for the bonding. That means cyanide should lose that negative charge. It's donating electron pair. But we don't count it that way. When we count the charges, like here, this is nitrogen with 4 bonds. Whenever we have a nitrogen with 4 bonds in the lone, actually not a lone pair. Whenever we have a nitrogen with 4 bonds, what's the formal charge? Like ammonium. What's the formal charge on nitrogen? It stops really soon. Ammonium is plus, and it has a net positive charge. Here, this is nitrogen with 4 bonds, but we're going to just consider it neutral, 0. So we count things differently. This is a cyanide. We should have went from -1 to 0, but we aren't going to do that. These are still cyanides. This is still a silver plus. And so we're doing something weird with the counting of electrons. And so we aren't going to count electrons like we did for all the other things. We count electrons differently for this. So actually, we don't even write these charges here. This whole thing is going to have a net minus. This whole thing is going to have a net plus. -1, -1, +1. And so normally we get rid of the charges altogether. And up to something like that. This one is named differently. This one's called dicyanoargentate ion. And so one of the nomenclature rules that we have concerns the metal. When we have a neutral or positive complex, neutral or positive, we just use the normal name. Normal name. When we have an anion complex, this is net -1 charge, then we use the Latin name. Well, not for all of them. One, we use the ate ending for all. But for some elements, we change it. And so, for example, if we had something like this, Al, let me write this over here. Al, I'll just write it like this, OH4, aluminum's 3+, and we have 4 hydroxide, so this whole thing is negative. This would be aluminate, and so we call this tetra hydroxo aluminate ion. So we just changed the ending to 8. There are just certain ones that we don't use. Like platinum, we can platinate. But silver would be called argentate in the negative complex. Tin would be called stannate. Lead would be called plumbate. Copper is just cuprium, so copper would be cuprate. See, are there any others that are fairly common? Gold would not be called goldate, it would be called orate. I think that's it. Okay, that's one thing. The other thing is, what we do is we change the name. So for example, this is cyanide. And then what we do is we change the ending. And so we use the O. So we drop the I, use O. This is ammonia, but we don't call it ammonio. We call it amine. And so this is amine. We have two amines, so this is diamine. There are some that have their name changed. The ones that have their name changed would be water, which we call aqua instead of water. Ammonia, which we call amine instead of ammonia. We have two types of amines, though. You know, the amine with one M, what was that again? We had amine with one M, which is the class of bases that are like ammonia. And then we have this amine, which is ammonia. This amine is not one M. This amine is two M's, like ammonia. Ammonia has two M's. And so this is not the class of compounds that are like ammonia. This is the actual molecule, ammonia, and it's spelled with two M's. CO, carbon monoxide, is given the name carbonyl. NO, which is nitric oxide, is given the name nitrosyl. Just those four have unusual names. Everything else would just retain its normal name. All right, let's stop here for a break. Take like a 10-minute break or so. And we'll start up again at, let's say 11:25. Yeah, 11:25. Yeah, so continuing on with 24.1 to 24.3. Are there any questions so far? Chris?
Yes.
Question? No? All right. This, we have this, something called the coordination number. The coordination number are how many bonds. So here, unlike the ethylene diamine tetraacetate, that would have a coordination number of 6 because there's 6 bonds to the metal. This only has a coordination number of 2. Now, how can you tell if something's going to have a coordination number of 6 or 2? Now, so for example, the lead ion had a coordination number of 6, but the silver ion has a coordination number of 2. Well, this is typical for silver. Silver typically has a coordination number of 2, but there are some metals that have more than one coordination number. For example, platinum. Platinum has a coordination number of 4 or 6. Now, we aren't getting into the theory. And so if we aren't getting into the theory, then we aren't getting the deeper description of what's going on. We're just looking at the observational data. And so based on observations, that's what we see. You know, platinum, coordination number of 4, coordination number of 6. Now, if you have a coordination number of 4, you know, we have two types of structures. And so let's look at the, that was linear. Then we have tetrahedral complexes. Tetrahedral would have a coordination number of 4, and aluminum forms tetrahedral complexes. So if we have aluminum like this, we can get 4 hydroxides on it. But when we bind a hydroxide, we change the name. Anions, you change the name to O. So I gets dropped, we call it hydroxo. Again, we do something weird with the charge here. Aluminum retains its 3+ charge, and the hydroxides retain their 1- charge. But when we look at this in counting formal charge, the formal charges on all these oxygens would be 0. So where's the -1 charge? Well, we just count things funny with complexes, so don't worry about it. It's just weird. And so what's the net charge? So if we have 4 hydroxides and 1 aluminum 3+, the net charge is -1. So this would be a tetrahedral complex. The coordination number is 4. Now, these bases, the Lewis bases, which we call ligands, these are monodentate. Although this could, like, for example, cyanide, there's a lone pair on the nitrogen. And you might think, well, if there's a lone pair on the nitrogen, can't this be a bidentate? No, there's no way this could be a bidentate because cyanide is sp hybridized. So the 2 lone pairs are on opposite side of the ion. In other words, in order for one to bond here, the other one's sticking straight out in the opposite direction. And so there's no way that you can bind both atoms. Now contrast this with ethylene diamine tetraacetate when we had the, let's say the nitrogens on the, we have one nitrogen bond and then another one wrap around. Well, this can't wrap around. It's a carbon-nitrogen triple bond. So these are monodentate ligands. Well, ammonia, there's only one lone pair, but cyanide had 2 lone pairs. And so it's either the carbon or the nitrogen. Well, carbon's better, right? Carbon's a better base than nitrogen. This is why the carbon end binded, not the nitrogen. Not only that, the carbon had the negative charge, not the nitrogen. The nitrogen had a 0 formal charge. And so this is monodentate cyanide carbon bonds. These are also, hydroxide's also monodentate. Even though I have 3 lone pairs, only one of those lone pairs are going to bind, not 3. And so monodentate here. Tetrahedral complex, and we call this tetrahydroxylaluminate ion. Now, we also have square planar complexes. Platinum likes to form, when we have 4 coordinate platinum, that is a coordination number of 4 on platinum, it likes to form square planar versus tetrahedral. Now, for platinum, square planar, I'm just going to draw it like this here, where I'm going to wedge dash this. And let's put in 4 means here. If I put in 4 means, like this, then we call this tetra. Now, I made a mistake over here. The mistake I made was I used the wrong number of M's. You got to remember, 1 M means something, 2 M's means something else. And so this should have been 2 M's because this is from ammonia. 1 M means it's a class of bases that are like ammonia, like methylamine, dimethylamine, trimethylamine. And so this is wrong. This should have been double M. Sorry, double M. Besides that. All right, so this is called tetraamine. So I'm going to have double vowel here. Tetraamine with 2 M's. And this is platinum. This is all one word. And the charge on platinum is 2. And so this would be the tetraamine platinum 2 ion, which is amines or ammonias are 0 charge, platinum's plus 2. Even though you think, oh, this is ammonia with 4 bonds. It's got to be like ammonium, with a positive charge, but it's not. We also have this complex, which is platinum. It's also square planar. No, when we have square planar in Chem 1A, you had a lone pair up here and a lone pair down there. This octahedral is sp3d hybridized. But there's no lone pair here and there's no lone pair there, according to Vesper. But these don't obey Vesper. These obey Vesper's valence bond. These obey MO. It's different. And so a lot of people are thinking, where are these lone pairs? They're missing. No, they're not there. And so here we have platinum. Let's put on 4 cyanide. Cyanide is an excellent Lewis base. Lewis bases we also call what? Ligands. So cyanide is an excellent ligand. Except, remember, what's the charge on cyanide? Platinum's still 2+. What's the charge on cyanide? Minus, 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 minus. It's kind of weird. But this whole thing is going to be charged what? Minus we'll call it 2 minus. Plus 2, minus 4, 2 minus. Now, naming this, these are cyanide, and whenever we have an anion that ends in I, we change the ending. So this is going to be tetra, which is 4, cyano, which is for cyanide, we drop the "ide" ending, tetracyano. Now, we don't call this platinum because this is an anion complex. With an anion complex, we call it, platinum, what's the Latin name for platinum? I think platinum. So it's just going to be tetracyanoplatin, not num, but platinate. Yeah. So whenever we have an anion complex, we have to have this 8 ending on here. And so tetracyanoplatinate, and then the charge on platinum goes in the Roman numeral here. This is all one word, tetracyanoplatinate 2 ion. All right, so we have tetrahedral, which is coordination number 4. Now, how do you know if it's going to be coordination number 4 versus coordination number 2? How do you know? We don't know. These are just observations. If you want to know, then you've got to dig deeper into the theory. We're not going to dig deeper into the theory. So these are just observational. And so you kind of look at it and you kind of get a feel for it, but you aren't expected to know. If I told you, what is the coordination number of this, I don't expect you to know that, because you would have to look at the data first and then determine it that way, because you don't have the theoretical foundation to predict it. And so just observational. So yeah, okay, then the observations are, we see a pattern. Platinum likes to form, nickel too. Nickel likes to form square planar. Aluminum likes to form tetrahedral. Now, there are differences, in aluminum ion versus platinum. The aluminum is a main group, platinum is a transition metal. That's one of the differences, And then we can think deeper into it, but we aren't going to think deeper into it. We're just going to look for certain patterns in reactivity, that's all, and patterns in complex formation. Okay, the next thing are the octahedral complexes. Now, one of the, there are two that are pretty common, what we call bidentate ligands. Just do this. And so let's look at some, most ligands are monodentate, most. Then we have 2 bidentate ligands, and then 1 hexadentate ligand. And so what are the 2 bidentate ligands? Let's talk about this, because in octahedral, I'm going to go bidentate maybe. And so the only 2 bidentate ligands you have to worry about, they're more than 2. And you can figure them out based on the structure. So bidentate, the 2 common examples would be ethylene diamine. Ethylene diamine is going to be H2N, CH2, CH2, NH2. And so one nitrogen binds, the other wraps around and binds. So that's a bidentate. So this is called ethylene diamine. Now, let's do this. Let's go with something like cobalt. I'm going to go with let's say cobalt, let's go with a cobalt 3 here. Now, these octahedral complexes are going to have 6 bonds to it, and so the 6 bonds, I should have done this first with the lead, is just draw an octahedral configuration of bonds there. Okay, then I'm going to put 1 ethylene diamine on here, and so I have to put them in adjacent positions. I can't put them on opposite, it's too far of a stretch. So if I put this 1 nitrogen on the top here, I can't put the 2nd nitrogen down on the bottom because it's too far of a stretch, too far of a distance. Yeah. So if I put 1 nitrogen on the top, like this, so I'll have an NH2 here, and then CH2, CH2, and then an NH2 down here. So do you see this? Now let's count the number of atoms in this ring. So this cobalt's 1, nitrogen's 2, carbon's 3, carbon's 4, nitrogen's 5. This is a 5-membered ring. 5-membered rings are not terribly strained. They're okay. And so ethylene diamine is fine. However, let's look at something like this. If I look at methylene diamine, methylene diamine is this. It's going to be H2N, CH2, NH2. So the difference between methylene diamine and ethylene diamine is 1 CH2. So if I knock out one of these CH2s out of here, how many atoms in the ring? 4. Is a 4-membered ring stable? No. 4-membered ring is not good. So methylene diamine would be regulated to monodentate, not bidentate. And so one nitrogen attaches, and it's hard for the other nitrogen to wrap around and attach. Does that make sense? With that? And so this should be a monodentate because of 4-membered ring. 4-membered ring is unstable. Monodentate because of a 4-membered ring, but it has 2 donor atoms, and so either side can attach. However, how about propylene diamine? So let's look at propylene. If we look at propylene diamine, propylene diamine would be H2N, CH2, 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 NH2. What do you think about propylene diamine? Well, how many membered ring? If I put in one more CH2 in this chain, then it would be a 6-membered ring. Is there any problem with a 6-membered ring? No problem at all. So this would be bidentate. What comes after prop? After prop comes butyl. Butylene diamine with no problem. 7-membered rings, no problem, etc. We could have those. But the most common would be ethylene diamine. This is an excellent one. Methylene diamine, propylene diamine, not that common. The next most common one would be oxalate ion, but let me continue with this. What I'm going to do is I'm going to put more. You know, how many more ethylene diamines can I fit? Okay, now I have 2 ethylene diamines. Can I fit 6 ethylene diamines onto this? This is octahedral, 6 coordinate. Can I fit 6 ethylene diamines? No, and in fact, I only have room for how many more ethylene diamines? I only have room for 1 more ethylene diamine, so it's going to be NH2, CH2, CH2, NH2. Okay. Now I have 3 ethylene diamines on this, like this. The way we write this formula is like this. We write it cobalt like this, and then we write the ethylene diamine. Ethylene diamine is kind of a long formula, so oftentimes it's abbreviated EN, and then we have 3 of those. Ethylene diamines are neutral molecules, and so this would be this. Now, how would I name something like that? Well, I'd like to name it like this. I'd like to call it triethylene diamine. Now note this amine. How many M's do I have on this amine? 1. You know, it's not ammonia. The only time you have 2 M's is when it's ammonia. And so this is triethylene diamine, cobalt. We don't need the 8. We can just call it cobalt. But we do need the charge, which is Roman numeral 3. Positive charge on cobalt. Okay, now, this is, take a look. This is a source of potential confusion. The source of potential confusion is that it looks as if I have 3 ethylenes and 2 amines. Do I have 3 ethylenes and 2 amines? No. Since this is a potential source of confusion, we have one more system. We're not going to call it tri to avoid confusion. Instead, what we're going to call it is tris. Tris for 2. And so we have a secondary numbering system. We have bi, di, 2, tri, tetra. Tri would be 3, tetra 4. The other name we have is this, tris. And so bis is 2, tris is 3. To avoid even more potential confusion, sometimes what we'll do is we'll put this in parentheses. So we'll call this tris ethylene diamine cobalt 3. And so here there's no confusion. I have 3 ethylene diamines. And so whenever the base or ligand has one numbering system, we have to use an alternate numbering system for numbering how many of those we have, the quantity that we have. We'll do some more examples. I can show you.
So what does it say? Triethylene, diamine.
This one on the bottom? This one? Yeah, this says triethylene diamine. But triethylene diamine, we're using the same numbering system for 2 different things. One, the di just represents 2 amines here on ethylene diamine. The tri is indicating 3 of those ethylene diamines. So we're using the same numbering system for 2 different things. We can't do that. And so we have to switch one of them. And so we'll just switch this one. So rather than saying tri 3 of these, I'm saying tris 3 of these. And the di is already part of the other name. So,
The ending of that.
I'm sorry?
How do you pronounce the end of that?
Cobalt 3. So tris ethylene diamine cobalt 3 would be the name. Let's do another one. Another common, ethylene diamine's the most common bidentate ligand. You're going to see this all the time. Since you see this all the time, there's shorthand ways of writing this. This gets kind of long. This is one shorthand way. Or cobalt, and then we can just write it, the whole thing out here. NH2, or H2N, CH2, CH2, NH2, 3. Well, we can write it out if you want.
Would it be triethylene diamine cobalt 3? Is that an ion or is it?
No. Oh, sorry. Yes, this is an ion. You can determine if there's an ion if there's a net charge. There's a net charge here because ethylene diamines are neutral, and the cobalt's still +3. So this thing has the 3+ charge. So, correct. We'll put ion here at the end. And ion here. Thanks. Yeah. The other common bidentate ligand is oxalate. Oxalate is C2O4 2-. And so the Lewis structure for oxalate is going to look like this. It's going to be like 2 of these carboxyl groups back to back. Now let me ask you this. What would you guess? Is this a monodentate, bidentate, tridentate, or tetradentate? It could potentially be a tetradentate. Why? Because I got 4 donor oxygens. 2 of these are better, but it's okay. 2 of these might be better, but actually there's resonance, so they're all in reality the same. What do you expect for this one? Bi, tri, tetra, dentate. Bi. This one's bi. And what happens is this. Do you think these two oxygens bind and these two don't? So if these two oxygens bind like this, how many atoms in the ring? And so here's the metal here. If these two oxygens bind, so this one boom, how many atoms in the ring? 4. Is that good? No, it's not good. These two versus these two would be better, right? Because the negative charge. If these two bind, then how many atoms in the ring? 1, 2, 3, 4, 5. That's good. But if these two bind, these are sp2, trigonoplanar. Is there any way for these two to bind? No, because they're on the opposite side of the ion. Like, there's no way for those to bind. And so it's a bidentate. Bidentate ligand. And let's do this cobalt 3. Cobalt 3 likes to form octahedral, so let's form an octahedral arrangement of bonds, like this. And then we're going to bond these here. So I'll go O, C double bond O, C double bond O, O. That's 1. Okay, then O, C double bond O, C double bond O, O. There's 2 of these bidentates. And then we'll throw on a third one over here. This would be 3. All right, what's the charge on this?
-3.
Yeah, okay. +3, -2, -2, -2, -6. +3 -6 is -3. That's correct. And so the charge on this is 3-. Normally, when we draw this out, we might show the positive charge on the cobalt. Usually we do. But on the ligands, we don't show the negative charges. Each of these are 2-. And so there's a lot of like conventions to this, and that makes it hard. But if you do a bunch of examples, then you get used to it. But how do we name this? How we name this is going to be this. Trioxalate, but we're going to change the ending from 8 to O. So we're not going to get rid of the 8, we're just going to get rid of the E and change it to O. And so it's going to be trioxalato. Now this is a anion complex, so we can't use cobalt. We have to add the 8 ending. So this is going to be cobaltate because it's an anion complex. And the charge on the metal is +3. So that goes in the Roman numeral +3. So this is called trioxalato, or oxalato, cobaltate 3 ion. Now, should I use tris here? I don't have to use tris here. Why? Because I don't have competing numbering systems. There's only one numbering system, so I could just use our standard numbering system here. So trioxalato, cobaltate 3 ion. So let's take a look at some examples. Still don't. More examples. see if they got my access to that. If you read the chapter, and normally I talk about this, I talk about Werner and this whole idea of complexes. This is more historical. Werner actually won the Nobel Prize for these structures because these structures perplexed chemists. You know, when they first came out, they had a totally different idea of how the ions and atoms were arranged, or molecules were arranged in this. And so let me give you the brief historical perspective here. You know, there are like hydrates, like waters of hydration. So, for example, if you had calcium sulfate, like what would calcium sulfate be in the hydrated? Penta? Probably penta or hexa. The amount of waters of hydration like if we look at calcium sulfate, you know, calcium sulfate is a white solid. But what happens is it's a desiccant, meaning like, you know, if you desiccants are like if you think of like an Egyptian mummy, or if you think of if you go out in the desert, you know, it's a desiccated environment, and so if there's any moisture around, the moisture is going to be picked up by the surface of whatever. The same thing with calcium sulfate. You know, we have different forms of it. One form is the desiccated form. The desiccated form is the anhydrous form. Anhydrous is no water, but it's like being out in the desert, you know? It's okay in a totally dry environment, but if you bring it closer to the coast and there's humidity in the air, what's going to happen is it's going to hydrate. When it hydrates, it picks up waters of hydration. And so calcium sulfate picks up 2 waters of hydration max. And so when it's hydrated, we call it this. And this is a solid, because where do those waters of hydration go? Well, calcium sulfate, what kind of structure is calcium sulfate? Crystal structure. I mean, what kind of solid is it? This would be the anhydrous form. It's an ionic lattice structure. So we got the sulfates in there and the calciums in there. It forms an ionic lattice like this. This is the anhydrous form. This is the hydrated form. And this is also the mineral gypsum, or this is, you know, in casts, the old plaster casts, or have this as well. Now, where are the waters in this? What happens with the waters is they get into the crystal. You know, water is polar. These are ions. There's attraction. So the waters squeeze into the crystal, into interstitial sites. These interstitial sites are like holes. Do you remember the holes in lattices? Like octahedral hole, tetrahedral hole, trigonal, planar, those kind of holes. Well, the water is thought to get incorporated into the holes in the lattice.
And so we could dehydrate this. You see waters stuck in the lattice. Do you see those waters stuck in there? You could easily dehydrate this. You know how to dehydrate this? Just heat it up. You heat it up, you're going to drive off the water molecules, steam. See that? Here it's hard to tell visually because they look so similar. Dehydrated and hydrated look similar. So when you look at it, it's hard to tell. Is that the dehydrated stuff or the hydrated stuff? It looks similar. Other ones, it's easy to tell. Both of these are copper 2 sulfate, but this is the desiccated one. This is the totally dehydrated one. And so if there's any moisture, it's going to pick it up and changes the color. So you can tell that this is kind of hydrated, even though it's dry solid. The waters are stuck inside the lattice. Even if it's 5 waters in there, this is the dehydrated stuff. It's easy to switch back and forth from the hydrated to the dehydrated. You know, if I want to dehydrate this again, I just heat it up. I'll get the desiccated stuff. And so what was thought is that the water ends up inside, you know, the holes in the lattice, the crystal lattice. And so when I dissolve this in water, it's going to free it up. Oh, calcium sulfate. Is sulfate soluble in water? It's a problem. Sulfates are soluble except for silver, lead, mercury, calcium, strontium, barium. This is not soluble in water. So I need to pick one that's soluble in water. Let me pick one that's soluble. In fact, let's go back to Werner and let's see what it is. So basically, if you think about water and ammonia, they're kind of similar in certain ways. What's one thing that water and ammonia have in common in terms of IMFs, intermolecular forces? Water and ammonia can both do what? And so you think IMFs would be intermolecular forces. So what types of intermolecular forces do we have? Hydrogen bonds, dipole, and London or dispersion forces. And so the thing between ammonia and water, well, they both can hydrogen bond. And so rather than adding water to hydrate it, we're going to add ammonia because ammonia, it's a gas. And so ammonia is very polar. And so those ammonia gas molecules are going to get stuck in the holes in the lattice as well, right? And so if they get stuck in the holes in the lattice, then this is soluble. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. Well, this is cobalt chloride, so it should be soluble. And so what I'm going to do is I'm going to take cobalt, so 2, cobalt 3, and cobalt 3 chloride, dot 6 NH3. And then what I'm going to do is I'm just going to take this solid and dissolve it in water. So I take this solid and dissolve it in water. What's going to happen is, well, it's a soluble salt. Soluble salts are strong electrolytes. Strong electrolytes dissociate into ions. And so what we're going to end up with is cobalt 3 plus 3 chloride, and then the ammonias are free to break away. You know, we could have gotten rid of the ammonias in 2 ways. One way, we could just heat it up. If you heat it up, you drive off the ammonia. The other way is you just dissolve it, and the ammonias are going to break free, but, you know, ammonia is very soluble. And so it should be aqueous. So all these three are going to be aqueous. Usually I don't write aqueous, but I'll write solid, liquid, gas. So one of the chemical, you know,
Well, keep going with what you were saying.
okay. What I was saying is, tell me some chemical properties of chloride. Chloride. Tell me some chemical properties of chloride. What's chloride? Yeah, it's a halogen. So actually, halogens usually reserved for the neutral, like chlorine. Chloride we would call halide rather than a halogen. And so halogens are very reactive. Halides aren't so reactive. And so chloride would be a halide. It's its base properties, negligible, right? It's such a bad base, we don't even really consider it a base. It's also a reducing agent, but as a reducing agent, is it very good? No, it's a pretty bad reducing agent. The only time it would react as a reducing agent is if we have a powerful oxidizer present, but other than that, it's unreactive. People eat it. They eat chloride, they drink chloride. There's chloride in tap water. Do you ever worry about it? Yeah. Don't worry about it. You know, each time you sprinkle salt on French fries, you're eating chloride. Do you ever worry about it? You don't worry about the chloride, but you might worry about the sodium ions, because the sodium ions will change your, electrolyte balance. The chlorides we don't worry about. Is that it? Let's see, that was redox and that was acid base. Is there anything else? Anything else? Metathesis. So what ions does chloride like? Silver, lead, mercury. So what they did was this. They wanted to analyze how much chloride's present. Well, that's easy. You take the chloride and then you add enough silver to precipitate it all out. And so we'll have to add 3 silver ions for every chloride. And then that's in the form of like silver nitrate. Silver nitrate soluble. It'll provide silver ions. And then we expect 3 silver chlorides, solids, to result from this. And that's what we expect, because that's, kind of what we think in terms of structure. But do you know what happened? Do you know how many silver chlorides they got? This was expected. How many did they get? They got 3 silver chlorides, as expected. 3 silver chlorides. That makes sense, right? Okay, now this is, 6 ammonia is the max you can fit in the holes in the crystal lattice. But we can do less than the max, right? We don't have to saturate. It's like a sponge. We could like have a half saturated sponge. Maybe half the sites are empty, right? Well, let's do this one. We're going to do this one. This is going to have 5 ammonia. So maybe there's an empty spot in the crystal lattice, right? And so we'll just put 5 ammonias there. And so let's do that here. So this will be cobalt-3 chloride, but .5 NH3s. So expose it to a little bit less ammonia. And then we dissolve that, H2O. And this should break up into the ions, cobalt-3 plus 3 chloride. And then the ammonia is set free from the lattice, because if the lattice breaks apart, we got the 5 ammonias there. Okay, now we're going to add excess silver nitrate to this. And so what we expect is this 3 chlorides plus, the excess silver. In other words, 3 silver ions. This should precipitate out 3 silver chlorides. That's what we expected, or they expected. Solid, expected. However, what was observed is different. You know how many chlorides was observed? What was observed is this. They only got 2. Two silver chlorides were observed. So what the heck is going on there? Because that's not what you expect. And so Werner won the Nobel Prize for this. He proposed a totally different structure than what you were thinking, or what people were thinking. And the totally different structure is this. This shouldn't be written like that. This should be written like this. Just erase this. In the penta ammonia one, pentamine, I guess you could call it, or something. The structure is like this. It's going to be cobalt. Okay, now I have to make sure I get this. They changed the rules, so I got to make sure I'm up to date with the current rules. So the structure is this. What this is a complex cation. This is a regular anion. This is just plain old chloride. And so I have 2 chlorides. And so let's take a look at the structure of this in more detail. The structure of this is cobalt forms a octahedral complex. Like this. We have 1 chloride, which we call chloro ligand. We have 1 chloro ligand and 5 ammonia ligands bonded to this with coordinate covalent or dated bonds. And so one of these chlorides is bonded covalently to the metal, 3+. This whole thing carries a charge of 2+. Chloride's still -1, cobalt's still +3. And so this whole thing carries a 2+ charge. And then what we have bonded to that are ions, the chloride ions, via an ionic bond. Ionic bond is just to put negative next to positive, and that's it. So I have 1 chloride over there and 1 chloride over here. So this is the solid lattice, and this solid lattice just extends off in 3 dimensions, etc. Okay, so this is solid. Now when I dissolve this in water, I dissociate the ions, but I do not break the covalent bonds. And so when you dissolve this in water, H2O, liquid, what's going to happen is I'm going to get this. And so this is dissolved in water. The ions break apart. So the cation breaks apart from the anion. The cation is this whole thing. COCl, NH3, Phi, 2+, and then I have 2 chlorides. And so I break apart the ions, dissociate the ions, but I'm not going to break the covalent bonds. And so in other words, these ions, the chlorides break off, and then I'm left with this. I'm left with the complex. This is going to be COCl. There's some abbreviations. Additional abbreviations are AM for ammonia. And oftentimes they don't write the lone pairs, but I like to write the lone pairs for additional practice. And then we have the chlorides, floating around here in solution. There's going to be translational motion of these, so they can move about. And so now when I dump in my excess silver, these 2 chlorides are attacked, right? Or the chloride attacks the silver, but this chloride isn't going to be able to precipitate out with the silver. Do you see that? And so this is what Werner won the Nobel Prize for, is he proposed complexes. That's got to be it. And so when you look at the lattice, this would be the crystal lattice here. You just have this gigantic cation here with the chloride alternating in some lattice like structure. So let's try to name some of these things. Now, some comments here. Okay, when we name an ionic compound, we name the cation first. And so this is what we call a complex cation and a normal anion. And so the complex cation name would be hexaamine. And so this would be, it's kind of weird because we don't say cobalt first. We name the ligands first. So it's hexaamine cobalt or cobaltate. It's cobalt because it's positive. And so hexaamine cobalt 3. I know it's plus 3 because I have 3 chlorides. So this would be called hexaamine cobalt 3 chloride. What would this be called? This would be the hexaamine cobalt 3 cation, or cation, and this would just be chloride, just normal. What would this be called? What would this be called? Because now I look at the cation, there are 2 different ones. I have chloro and amine. So which one should I name first? Should I name the chloro first or the amine first? And the rules have changed. And so when you look at things online, you could see them from the past, and they're named differently than the present. Okay, but the way we're going to name this is we're going to name the ligands in alphabetical order. Now, it's going to be alphabetical not according to the name, but according to the symbol, the element symbol that it's normally written. And so this is all screwed up because sometimes we write NH3 like this, and sometimes we write NH3 like this. And so what do I base NH3 on, nitrogen or hydrogen? As far as alphabetical order goes. So I don't really like this system. I would rather have it based on the name. The name would be amine, and amine, it's A, so it doesn't really matter. But here, we're gonna base it on the nitrogen. So, so this one gets named first. This would be chloro pentaamine. Chloropentamine cobalt 3 chloride. It's still cobalt 3, even though the whole thing's 2+. But let's look at a lot of examples. So I'll go through these quickly and then get them break down. Okay, this would be hexaamine cobalt 3. Pick that up. Now we have the chloro and the amine. So this one's going to be tetrachloro diamine cobalt. Okay, so this is -4 plus 3 gives us -1. So this has got to be cobalt 3. So tetrachloro diamine cobalt 3. This one would be trichloro triamine cobalt 3. Okay, now this is an anion. So this is a normal cation, this is potassium. So this would be potassium, and then what's the anion name? This one would be hexacyano ironate, iron, or ferrate. Ferrate, that's one I forgot. This is hexacyanoferrate, and what's the charge on iron? So this is +4 because each one's +1. So +4, this has got to be -4. The whole thing's -4. And then cyanide is -1. We have 6 of them. So -6 plus what gives us -4? +2. So this has got to be iron, or not iron, ferrate, Roman numeral 2. Okay, I talked about coordination number, and this is just the data. You know, how do you predict? Well, we look it up in a table at this point. So you aren't expected to memorize this, but you know, you want to look for patterns, as then we get some idea as far as the data goes. But as far as coordination number goes, you know, copper +1 is 2, 4. Actually, copper 2 is more common. Here it is. Copper 2 is 4, 6. Copper 1 complexes, there aren't that many. Silver is 2. Gold is 2, 4. Iron 2 is 6. Cobalt 2 is 4, 6. Nickel 4, 6. Copper 2, 4, 6. Zinc is 4. Platinum is 4. Aluminum is 4, 6. Scandium 6. Mostly 6s, don't you see? Mostly octahedral. Now, if we have 4, we have a choice. 4 could be tetrahedral or it could be square planar. I don't know. You know, when I look at this, I don't know which of these 4 are octahedral and which are square planar. Actually, I do know because I've looked at the data table. And so I do know that platinum likes square planar. But that's just memorization. Zn2 plus likes tetrahedral. Zn2 plus is special because it's D10, you know, electron configuration, 3D10. A lot of these others have partially filled d orbitals. But anyway, aluminum 3 plus likes tetrahedral. You know, it's just memorization at this point. Later on, you'll know certain features that help you, like nickel 2, you know. When we get into the theory, which we will get into more theory at the end of the chapter, it might make more sense. 6 is only octahedral, so, you know, we have a choice. 2 is always linear. 4 might be this one or this one. 6 is always this one. They're more, but we aren't going to get into the more. Now, sometimes to figure out the coordination number is simple, sometimes it's more difficult. For example, this one, what's the coordination number here? Whenever somebody asks you what the coordination number is, you have to look. Is it a monodentate ligand, bidentate, hexadentate? We need to know that because it's not always the number of ligands. Sometimes it is. In this case, you know, chloride is mono or chloro. This is nitrite. Nitrite we call nitro or nitrito. And so that has 2 oxygens and a nitrogen, so that could be bidentate, but you're thinking, if it were bidentate, let's say the nitrogen and the oxygen, then it would be too small of a ring. You see that? And so this has got to be mono. If it's mono, what binds? Does the nitrogen bind or the oxygen bind? If it's mono, actually either can bind. And so we have 2 nitritos. We have nitrito-N, nitrogen binds, or nitrito-O, oxygen binds. And so we could have either. Although you would think nitrogen should be better, but the nitrogen is going to be less negative, more positive in this case. And then we have amine. Okay, so this is actually 6 coordinate. We have 6 monodentate ligands, so the coordination number is 6. What's the charge on the cobalt? The charge on the cobalt is the oxidation state. And so let's figure out the charge. The whole thing adds up to +1. Ammonias are neutral. Nitrite is -1, chloride is -1. So -1, -2, -2 plus what gives us +1? +3. So cobalt's got to be +3. +3 -1 -1 gives us +1. Okay, and it's 6. So coordination number 6 has got to be octahedral. How do you name this? Let's try to name it. So we have CNN. Okay, this is NH, this is NO. So we'll probably go C, NH3, NO2. We're going to name these alphabetically. Now, why did they order it like this? I don't know. You know why they ordered it like that? Why didn't they order it alphabetically? If we're going to name this alphabetically, why didn't they order it alphabetically? So if we name this alphabetically, it would be, which one would go first? C, chloro. Next would be NH, amine. So chloro, tetraamine with two M's. Nitrito. Now there's two ways of writing nitrite. If the nitrogen binds, we write it NO2. If the oxygen binds, this screws it up the alphabetical soon. You know, let's just do alphabetical based on name. Because this would change its ranking alphabetically, but it probably doesn't matter anyway. So this is oxygen binding, this is nitrogen binding. Both of these are nitrite. So I know that this is nitrogen binding because of the way it's written. And so we would call this chlorotetraamine nitrito hyphen N hyphen cobalt, it's positive, cobalt 3 ion. So that would be that. Let's look at some other monodentate ligands. There are a bunch of monodentate ligands here. We had, oh, they changed the name of this one, sorry. You still see nitrosyl for this one all the time, you know. But nomenclature's evolving because, you know, it's hard to get chemists to agree on stuff, and we get into arguments about these kinds of things. But this has been aqua for ages. This is amine with two M's. This is carbonyl. So they didn't change that one, but they changed this one from nitrosyl to oxido nitrogen. Oxido nitrogen. This one is methanamine. Methanamine. This used to be methylamine, and you just use methylamine, the name of the molecule, rather than changing it. Pyridine, this is actually pyridine. Fluoride is fluorido, chloride is chlorido, bromide is bromido, iodide is iodide, oxide is oxido, hydroxide is hydroxido. Yeah. Cyanide is cyanido, sulfate is sulfato. Sulfato is monodentate, otherwise the ring would be too small. Thiosulfate is thiosulfato. This is nitrito hyphen N hyphen. This is nitrito hyphen O hyphen. This is thiocyanide hyphen S. This is thiocyanide hyphen N. So S and N can both be binding here. Those are some common monodentate ligands or bases. Here you can see, you know, methanamine, I still call this methylamine, and you still see a methylamine everywhere. That's all right. This is, do you recognize this one? What is this one? The most common bidentate ligand there is. What is this one? Ethylene diamine. Bidentate ligand. Anything bidentate or bigger is called a chelating agent. And so these are three chelating agents. Chelating agents are awfully hard to break off. These are the three most common ones. Ethylene diamine is number one, by far the most common. Oxalato, second most common bidentate ligand. And ethylene diamine tetraacetate or ethylene diamine tetraacetato is not a bidentate. What is this one? Hexadentate. So 4 minus here. This is 2 minus. Ethylene diamine is neutral. We abbreviate the formula for these, but we don't abbreviate the name. So when you name it, you write out the whole thing, the whole name. When we write the formula, sometimes it's a hassle. So let's take a look at the earlier one. Let's name it. So the earlier one I tried to draw lead. Now lead is written first, and then ethylene diamine, but we don't write the whole name. We just call it EDTA in the formula. What's the charge on this one? This is a lead 2. So if this is +2, what's EDTA? -4, so the whole thing's going to be 2 minus. And the way we name it is we spell the whole thing out. Even though I abbreviated in the formula, which is okay, I have in the name I can't abbreviate it. I have to spell it out. And it's going to be ethylene diamine. Is this 1M or 2M's?
1M.
1M. Ethylene diamine tetra acetato.
Can you remind me how to tell if it's 1M or 2M?
Well, only ammonia, only NH3 gets 2 M's. Everything else just gets 1 M. Ethylene diamine tetraacetate, lead or leadate or plumbate? Plumbate. Roman numeral 2. Roman numeral 2 is for the +2 charge on lead. Remember, we didn't lose the +2 on lead. And it's -4 on EDTA. And so that would be ethylene diamine tetraacetate plumbate 2 ion. This will neutralize the lead in your bloodstream, because it forms, a chelating. This is the best chelating agent to encapsulate it, and then you can excrete it some way. What's the coordination number of this? Platinum. Well, you look at this, some people will say, hey, the coordination number is 2. Some people will say the coordination number is 2 because I have 2 ethylene diamines. Do you see the 2 ENs there? So they say there's 2 ethylene diamines, therefore the coordination number is 2. Is that true or false? That's false. What is the coordination number? 4. The reason is because each ethylene diamine is bidentate. So here's a ball and stick model. This is the shorthand way of doing it, but this is kind of weird because we don't draw the square here. We draw these lines, these 4, and then the ethylene diamine you draw as a loop here on the end and call it EN instead. It's a very common ligand. Here are the rules for nomenclature of these. So you can go through the rules and figure it all out. We'll just look at examples. Here are some of the names that we change. Iron, in anions, ferrate, cuprate, stannate, argentate, plumbate, borate. I just missed ferrate, I think. Forgot that one. Sometimes we have neutral metals like this. Let's name this one. This is WCO6, neutral. Carbon monoxide is neutral, so that means tungsten is neutral. So this is hexacarbonyl tungsten 0. There's no charge on that tungsten atom. So it's just a neutral metal atom stuck there. Yeah, you have to write the 0. It's neutral. That is the metal. The complex could be a charge. The complex itself could be neutral, but the metal could be charged. Okay, so let's take a look at some more problems. Why don't you guys try these ones out? Can you read that, or is it too small? Too small? All right, so number one, give this one a try. Write the formula and name of a complex ion having chromium 3 plus as the central ion. The central is in the middle of the complex. And 2 ammonia molecules and 4 chloride ions as ligands. Ligands would be the bases. Attach that. And so give that a shot.